شما رو و ان شاءالله زحمت میدیم که شروع کنیم وبینارتون. So I would like to say hi to all the participants in our weekly webinar at the Industrial Engineering Department of Sharif University of Technology. We have the honor of hosting Dr. Saeed Qadimi today on stochastic composition optimization. I would like to ask all participants that if they have any questions or any points regarding Dr. Qadimi's presentations, to keep your questions at the end of his presentation. We will give around 15 to 20 minutes time for a Q&A session. Dr. Qadimi, is 1 hour enough for your presentation?
Yep.
Okay, that's great. So I would just like to switch to Farsi to say hello to our Persian speaking participants. But before that, I would like to introduce Dr. Qadimi. Dr. Qadimi received his bachelor's at Sharif University of Technology at the Industrial Engineering Department, and currently he's assistant professor at the Management Sciences Department of the University of Waterloo, with his research interests being particularly focused on reinforcement learning and optimization methods based on learning problems. But of course, I would like Dr. Qadimi to introduce himself in a more complete way at the start of his webinar. So I'll switch to Farsi, then Dr. Qadimi can start, and as I said, we can have the QA session at the end. So thank you for your patience, and I apologize for the couple of minutes of delay we had. خب من سلام عرض میکنم مجدد خدمت همه دوستانی که تو این وبینار حضور پیدا کردن. من خواهش میکنم که دوستان هر گونه سوالی یا نکته در مورد ارائه آقای دکتر دارن در پایان وبینارشون 10 دقیقه الی 15 دقیقه فرصت میدیم که این سوالا رو بتونید از آقای دکتر بپرسین. حالا چه بخواید تایپ کنید من میخونم برای دکتر سوالا رو، چه اینکه بخواید میکروفونتون یا حتی وبکمتون فعال شه که رو در رو سوال کنید. دوستان هم که اگه تو پرسش سوالشون تو زبان انگلیسی مشکل دارن میتونن سوالشون رو فارسی بفرمایید. حالا شاید یه ترجمه کنیم که اگه شرکت کننده بین‌المللی هم داریم اون دوستان هم در جریان قرار بگیرن. حالا برای مهمونای خارجی میگی من ترجمه میکنم دیگه، برای دکتر نیاز نیست که من سوال شما رو فارسی ترجمه کنم، میگیم که دوستان هم بتونن استفاده کنن. خب همونجوری که من به انگلیسی هم گفتم آقای دکتر که از خودی هستن، لیسانسشون دانشکده صنایع دانشگاه شریف بودند و دکتراشون اگه اشتباه نکنم دانشگاه فلوریدا طی کردند و الان استادیار دانشکده علوم مدیریتی دانشگاه واترلو هستند. Okay, Professor Qadimi, again I thank you for your time and we're at your disposal.
سلام به همه. Thanks Muslim, thanks to the IE department for the invitation. So I just stopped the video to share the slides. So today I'm going to talk about stochastic composition optimization. My main research lies in the area of decision making under uncertainty and with the focus on the non-convex stochastic optimization. Okay, so here is my problem of interest. So we want to minimize function f, which is a composition of two or more functions. So here, each function fi, we assume that it is continuously differentiable, and we assume that this feasible set x is closed and convex. So in this talk, I focus on the setting, on the stochastic setting, where neither values nor derivatives of fi can be observed. In particular, we assume that each function fi is given through an expectation. So for any point y, we assume that fi at y is given as expectation of another function gi at y and random variable psi. And we just assume that we can observe the random variable psi to estimate the values and gradients of each function fi. Now let's look at some examples for this class of problems. Maybe this is a better way to do it. Okay, so the first one is sparse additive models. So assume that we have a sample data points xi and yi, which are given with this form. So yi is the summation of some feature component function plus some zero mean noise. And assume that you have some pre-specified functional space H for these feature component functions. Then in the sparse additive models, you want to estimate the feature functions hi by solving this problem, this minimization problem. And as you can see, the second term here can be written as a composition of the the square root function and an expectation. The second example, I don't know why I should do this every slide, is for the policy evaluation for MDPs. Assume that you have a Markov chain with unknown transition operator P and a reward function R. So we can estimate the value function by solving this equation, which is the weighted average of the rewards. So if we write this in a vector equation, then we want to solve this larger scale Bellman equation. However, when the size of P is large and R is not known, it's almost impossible to solve this problem exactly. So people have tried to estimate this value function. So in this case, one can employ a sketching matrix and a linear model for the value function to estimate the value function in this way as the weighted average of these basis functions. And so then you can solve the Bellman residual minimization problem to estimate the value function. And as we can see here, this can be seen as a composition of two functions, the norm squared and an expectation, a linear term inside the norm squared. The next example is low-rank matrix estimation. Assume that you have a matrix X bar, you don't know that matrix, and you want to estimate it. So one can sample from an unknown matrix, and each sample give you an unbiased estimator for this unknown matrix. So assume that K is much less than D to be a pre-specified rank for the matrix. Then the low-rank matrix estimation is formulated in this way. So here L is the loss function, which can be the Frobenius norm or any other kind of norm. And you want to minimize these for U and V, which are assumed to be low rank. So as you can see, this problem is another example of composition problem. You have an expectation inside the loss function, which can be any loss function. The next example is minimax problems. So in stochastic games with random payoffs against an adversary or opponent, you want to solve this minimax problem. So in this problem, this is another example of the stochastic composition problem. However, the max operator here is not a smooth function. So one can just use the available smooth approximation to estimate this max operator with the smooth function. Then this would be an example of the stochastic composite optimization where both inner and outer functions are smooth. The next example is risk-averse stochastic optimization. So you want to minimize the mean deviation, or in this problem, maximize the mean deviation. So as you can see here, the second term here, the deviation from mean, can be written as a composition of three functions, essentially. The whole function here can be written as an example of composition of three functions. So the previous examples were essentially composition of two functions, but these three examples assume that you have more than two functions. The other one is the multi-stage stochastic optimization, that you want to solve this problem. If you assume that the random process comes from a random walk with finite states, then the multi-stage stochastic optimization can be reformulated as the stochastic composition problem. And the last example that I want to present is compress sensing. So let's look into the details of this example. So assume that you have signal X star that you wish to recover. So we are allowed to observe measurements of the form, the linear the linear transform of this X star. So A transpose X star plus noise. So here A is the random measurement vector and E is the noise in the measurement. So in the classical formulation, you want to minimize this objective function, assuming that X, the true signal, only had K non-zero component. So recently, motivated by the success of deep learning, people proposed a generative approach to compressed sensing. So in this reformulation, there is a latent signal vector Z star, such that for a given neural node G, the true signal is given by G of Z star. So in this case, true signal is assumed to lie in the range of a neural network, given the latent signal Z star. Again, we are allowed to observe measurements of the form A transpose. Here, instead of X star, it is essentially X star, but it is in the form of G of Z star plus some noise. So this problem then can be reformulated in this form. So the mapping G is assumed to be a deep neural network with depth T. So in other words, it can be written as a composition of T functions. And each component of the function can be written as expectation of the activation function. So here, the expectation is taken with respect to this function rho of G and B, which is a distribution over the weight and the bias at each layer of the neural net. So this activation function can take different forms, but there are examples of a smooth activation function that you can use to make the problem smooth. And if it is not smooth, you can just use the smooth approximation of those activation functions. So this problem will fit in our setting. So in the rest of this talk, I first review some related works on the stochastic composition optimization. Then I will talk about algorithms for solving the two-level case, when you just have a composition of two functions. And then I will talk about the generalization to the multi-level case, that you have more than two functions. So interest in stochastic approximation algorithms for solving this composition problem dates back to 1976, where the penalty functions for stochastic constraints and composite regression models were considered. So the main approach was to use two or multi-level stochastic recursive algorithms in different time scales. Essentially, for the two-level case, two step-size sequences were used, one for updating the main decision variable and another for the filtering the value of the inner function. Remember that the difficulty for solving this composition problem is that even if you have an unbiased estimator for both outer and inner function, you will not get an unbiased estimator for the overall function. So you cannot apply the classical stochastic approximation algorithms, which mainly assume that you have an access to an unbiased gradient estimator for the gradient of the objective function with bounded variance or second moment. So in this class of algorithms, the key point is that the outer method must be infinitely slower than the inner method. And in this case, you will get a worse convergence rate than the classical stochastic optimization. So recently, over the past few years, studying finite time convergence of SA algorithms for solving this composition problem has gained more interest. So people have tried different settings to come up with the finite time convergence of the stochastic algorithms. These works provide sample complexity result by assuming different convexity assumptions, either the outer or inner function are convex or they are generally non-convex. However, all of the complexity results are worse than their single-level stochastic optimization counterparts, meaning that you just want to minimize a single expectation, not the composition of expectation. So there was a recent paper on the central limit theorem for this stochastic composition optimization. And people have shown that the D-sample empirical optimal value of the problem converges to the true optimal value at the rate of 1 over the square root of D. So we know that this is the rate for the classical stochastic optimization. People have shown that we can get the same rate for the central limit theorem when you have a composition problem. So this motivated us to come up with an algorithm that can recover the sample complexity for the single level problem. So when it is allowed to take mini batches, people propose a sampling scheme to obtain unbiased sample gradient of the objective function. However, the variance of this unbiased estimator polynomial depends on the problem dimension. And then when you have a large scale problem, you cannot use this approach to estimate the gradient and then apply the classical stochastic approximation algorithm. So more recently, we have proposed a single time-scale stochastic approximation algorithm for solving two-level case, which I'm going to present today. And the convergence of this algorithm is the same for both. The convergence does not depend on the level of the problem. So we recover the optimal rate. So I will describe about this in the next few slides. But for the multi-level case, there are some more recent work. So for example, people have shown that they can obtain the sample complexity of t to power 6 rho to power t divided by epsilon q. So I will talk about this sample complexity later. But to obtain this sample complexity, they assume a strong mean-square Lipschitz smoothness on the individual functions fi and their gradients. They also assume that for a fixed batch of samples, one could query the oracle on different points, which is not an appropriate assumption for the general online stochastic optimization setup. Moreover, to obtain this result, they assume that they need to take a mini batch of samples, which cubically depends on the number of layers. When T is moderately large, then at each iteration, you have to take many samples, which is not a good idea. Also, there is another work for multi-level case that the author provides asymptotic convergence of the proposed algorithm to the stationary point of the problem by analyzing a system of differential inclusion, which requires the compactness of the physical set. So in many applications, the physical set is essentially unconstrained. So this compactness limits the applicability of this algorithm. Moreover, the finite time convergence of this algorithm is not given. I mean, it is given, but it is not complete, so we cannot say anything about that. So now let's first focus on the two-level case. So here's our problem of interest. So for the sake of notation here, for these two functions, I just use f and g. So we want to minimize f of g of x. So the main idea of our algorithm is, instead of just looking for the stationary point, to lift the problem into a higher dimensional space. So in this case, our goal is not only to find the optimal point x, in this case, the stationary point x, since we are considering the non-convex problems, but also to find the gradient of f at that point and the value of the inner function at that point. So in this case, we can construct an iterative method by using just one step size sequence, which enables us to provide the optimal convergence result for this algorithm. So here is the algorithm, the nested average stochastic approximation, which we call it the NASA. So here we first solve a quadratic subproblem at each iteration, and then we take the weighted average of the solution to the subproblem. Then this decay here, so in the classical stochastic approximation algorithm, this is just a stochastic gradient. But in this algorithm, it is a weighted average of the stochastic gradient. which is not an unbiased estimator of the gradient at point xk. So this is the two difference between this algorithm and the classical stochastic optimization algorithms. In addition, we have a sequence UK which tracks the value of the inner function, G. So since we don't have the exact value of the inner function, G, we need to estimate that values to be able to compute the gradient of the objective function at that point. And then the output of the function would be XR and ZR. So here R is a random variable based on the probability mass function. So as you may know, for non-convex stochastic optimization, for convex stochastic optimization, one can output the weighted average of the generated sequence, or essentially the convex combination of the generated sequence. However, this is not the case for non-convex problem because the convex combination does not make sense. So the current practice to establish the finite time convergence of any stochastic approximation algorithm when applied to non-convex problem is to output a random index. So instead of outputting the convex combination, we just output a random index, which the probability mass function of this random index depends on the choice of the step size of the problem. So here, our algorithm generated three sequences: the approximate solution xk, the weighted average of zk, and the weighted average of the inner function value uk, which are all defined on a certain probability space. And here, we assume that all xk, x naught to xk, z naught to zk, and u naught to uk form the sigma algebra for this algorithm as we run it for the k iterations. So here our first assumption, so we need this assumption to establish the convergence result of the algorithm. So we assume that we have an unbiased estimator for the inner function value. We have an unbiased estimator for the inner function gradient, and we have an unbiased estimator for the outer function gradient of the outer function. And we assume that their second moment or their variance are bounded. So these are just normal assumptions in the stochastic optimization. But if you look at here, as you can see, while we have the unbiased estimator for the gradients and the value of the inner function at xk plus 1, the gradient of the outer function is computed at the uk because we don't have this value of the exact value of g of xk plus 1. So in other words, while we have the unbiased estimator for the gradient of f and g, we don't have the unbiased estimator for the gradient of f og, which is the composition of these two functions. And that's the main difficulty for this class of problems. So here is the simple result about the optimality condition of the problem. So if a point x is a local minimum of the composition problem, then we know that the negative of the gradient should belong to the normal cone at point x, x hat, if x hat is the stationary point. And if the problem is convex, this would be the global minimum. So now let's look at the optimality condition based on the subproblem that we solve at each iteration. So let's name the solution to this subproblem as y bar of x, z, and beta, which is essentially the Euclidean projection of x minus z over beta over the feasible set x. So the relation that says negative z belongs to the normal cone at x is equivalent to say that y bar equals x. These two are equivalent. So if z bar is the gradient of f at x bar, then this would be the stationary point of the problem. Using this observation, we can define our measure of violation of the optimality condition by primal dual pair of x and z. So we can define function v of x and z as the difference between x and y bar plus the difference between z and the gradient of f. In the simple case, the unconstrained case, when x is Rn, this would be just an upper bound on the size of the gradient. Then we can define an epsilon stationary pair of the problem as the pair of x and z such that the expectation of the root of v of x and z is bounded by epsilon. So here, in the definition of v, we assume that beta is 1, but we can simply show that the difference between x and y bar when beta is 1 is scaled by the max of 1 and beta when you use beta in the subproblem. And then accordingly, we can get an upper bound for this measure of the violation of the optimality condition. So here is the comparison of our measure of violation of the optimality condition and two different criterion used in the literature. So the first one is the proximal point mapping. So this one, assuming that y bar is the solution to this subproblem, then the proximal point mapping criteria is y bar minus x hat squared. So in this case, by defining z hat as the gradient of f at y bar, we can easily show that our choice of v of x and z hat is bounded between y hat and x bar, difference between y hat and x bar squared, and a constant times y hat minus x squared. Similarly, the other criterion is the gradient mapping, which assuming that y tilde is the solution to this subproblem. So here, the proximal one, it was f. Here, this is just a linear product of y and gradient of f. In this case, defining z bar as the gradient of f, we can show that our choice of optimality measure is the same as the gradient mapping. However, for both cases, this z hat and z bar are not computable under a stochastic setting. But in our case, z is computable, and it is essentially an online estimate for the gradient of the objective function. So here is our next assumption. So we assume that the function f and g and their derivatives are Lipschitz continuous, and then simply we can show that the gradient of the composition function is also Lipschitz continuous. Similarly, we can show that the optimal value of the subproblem is also Lipschitz continuous. We use these lemmas into improving the convergence of the algorithm. So here is the main convergence result for the NASA method. So assuming that the beta k is beta, the parameters a and b in the algorithms are just simply 1, and the step size tau k is 1 over square root of n, which n is just a given number, then we can show that the total sample complexity of this algorithm to find an epsilon stationary pair of the composition problem is bounded by 1 over epsilon to 4. And this is the same sample complexity to estimate the value of the inner function. So this 1 over to epsilon 4, we know that it is optimal. I mean, people recently have shown that it is optimal for the single level problem. And it is clear that any lower bound for the single level problem would be a lower bound for the composition problem. And here we achieve that lower bound. So this lower bound, this upper bound here is optimal for solving the composition problems. Before this method, the best known complexity was 1 over epsilon to 4.5. And just for unconstrained case. But our method, the convergence analysis of our method is the same for both constrained and unconstrained cases. And it does not require to take any batch of samples per iteration. It is also consistent with the central limit theorem that we can recover the same rate for the sample average approximation of the composition problems. Here is the asymptotic convergence of the algorithm. So we can show that if tau k, if you want to run the algorithm for many iterations and tau k satisfy in these two conditions, then the sequence xk, zk, uk converges to the x star, z star, u star, such that z star is the gradient of the composition function at x star, the negative z star belongs to the normal cone at x star, and u star is the value of the inner function at x star. So let me just simply go over the convergence proof of this algorithm. So we define a merit function in this way. So the difference between f of x and f star, so for non-convex problem, this f star is just a lower bound on the objective function. This eta is the optimal value of the subproblem, and this is the error in estimating the inner function. So we can show that by properly choosing the parameter beta k, we can get this recursion formula. So the difference between w at k plus 1 minus w k is bounded by this one, which r k plus 1 is fk measurable here. Then if you sum up these inequalities and rearrange the terms, we get something like this. So we can show that the difference between yk minus xk, remember that yk is the solution to the subproblem. And gk minus uk estimates the value of g at xk, is bounded by this quantity, which rk plus 1 is fk measurable. So if you remember the measure of the optimality condition, so now we bounded the first term here, as you can see here. And the second term, the difference between zk and gradient of f at xk, we can show that it is also bounded by fk measurable terms. And then when we take the expectation, we get the result as I showed you. So let's quickly look at the special case when G is just a linear map. So in this case, essentially we are considering the classical stochastic optimization. We just have expectation of f of x. In this case, the algorithm is the same. However, we don't need the sequence uk to estimate the value of the inner function, because it is exactly known. So g of x is just x. So the only difference is that we just remove the sequence uk here. And as expected, the complexity result of this algorithm is the same as the NASA method. It is 1 over epsilon to 4. And assuming that the second moment of the stochastic gradient is bounded, this algorithm is parameter free. So in the NASA method, for the two-level case, we had to choose beta k properly, and the choice of beta k depends on the problem parameters, like the Lipschitz constants. However, for the single level case, the algorithm is parameter free. That beta can be set to just 1. However, if we reduce the assumption from the boundedness of the second moment to the boundedness of the variance of the stochastic gradient, the algorithm still obtains the same sample complexity, but it is not parameter free. Then the choice of beta k will depend on the problem parameters. So in the rest of talk, let's talk about the generalization to the multi-level case. So far, I talked about the two-level case. Now let's see what happens if you have more than two functions. In this case, direct generalization of the NASA method does not converge due to the accumulated error in estimating the inner function values. So to resolve this issue, we consider two approaches. The first one is using mini batch of samples, and the second one is using the first order approximation of the inner function, as I will describe in the next slides. So here is the case that we use the mini batch of samples. So the algorithm is the same. So the framework is the same. as NASA. So we solve a subproblem, quadratic subproblem. We take the weighted average of the sequences. We take the weighted average of the stochastic gradient. So here, instead of the two-level case, we have the multiplication of t stochastic Jacobians of the inner functions. And instead of just tracking the value of inner function, one inner function here, we have t minus 1 inner function. But in general, it is written for 1 from 2. We don't need the value of the outer function, but this is just for the sake of notation. So we track the value of the all functions. But the difference is here. So instead of gi, we have g bar, which g bar is the average of some gi and j. So for a given point, wi plus 1k, we compute the function values of fi, the estimate of fi, bk times. At iteration k, we compute the function values bk times, and then we take the average, and that we use that average here to estimate the value of fi. So here, instead of 3 sequences, in the two-level case, we have t plus 1 sequences. As I mentioned, when t equals 2 and bk is 1, there is no Bini batch. This algorithm reduces to the NASA method. Again, we can define the sigma algebra based on the random sequences generated up to iteration k. And we can modify our assumptions in this way. So again, we assume that we have an unbiased estimator for the Jacobians of the inner functions. We have an unbiased estimator for the value of the inner function, and their second moment and their variance are bounded. We also assume that the outputs of the stochastic oracle at each level I, gi, the value, the estimation for the value function, and ji, which is the estimation for the Jacobian of the fi, are independent. So we make two independent oracle query. And we also assume that the output of the stochastic oracles are independent, meaning that for G1 through GT, these are also independent. So GI and JI are independent, and GIs between levels and JIs between levels are independent. So we just make the independent queries to the stochastic oracle. So we have a similar assumption here. The function fi and their derivatives are Lipschitz continuous. And so we can show that under this assumption, the function f, the composition function, is also Lipschitz continuous. So here is the main convergence result for this algorithm. So we can show that if the previous assumptions hold, then by properly choosing the step size or the parameter beta k, and setting tau k 1 over square root of n, which is same as the NASA method, and having this mini batch pk as 1 over tau k, which would be in the order of root n, then to find an epsilon stationary point of the problem, we need rho t times t to power 6 divided by epsilon to 6. For this problem, we need 1 over epsilon squared, samples per iteration, to reduce the variance associated to the estimation of the inner function values. And this is the same sample complexity in estimating the inner function values. So if we compare this result, as you can see here, there is no dependency between t and epsilon. But the best known result was 1 over epsilon to 7 plus t divided by 2. So there is a direct dependence here. When epsilon decreases, then this sample complexity increases exponentially. But in our case, it is 1 over epsilon to 6. However, it is worse than the rate for the classical or the two-level case, which is 1 over epsilon to 4, and that's due to the batch of samples, which was in the order of 1 over epsilon squared. So this algorithm exhibits a level-independent behavior, meaning that there is no direct dependence between epsilon and t, the number of levels. However, it requires batch of samples per iteration. But there is a way to fix this issue. So this algorithm is the same as the previous algorithm. The only difference is here. So instead of taking mini batch of samples in estimating the inner functions, we add a linear approximation of the function values as well. So this Ji is the estimation for the Jacobian of Fi, and this is the difference between Wi plus 1k plus 1 minus Wi plus 1k. So this Ji is the Jacobian computed at Wi plus 1k. So by adding this linear term here, we can remove the need of batch of samples per iteration. However, we need a stronger assumption. So before stating the assumption, I should mention that this algorithm is motivated by a recent paper by Andrzej Rosinski. However, in this paper, as I mentioned before, the assumption is that the feasible set is bounded and there is no finite time sample complexity result. The convergence result is the asymptotic convergence. So by assuming that we have unbiased estimator, but their force moments are bounded instead of the second moment, which can be satisfied if the random vectors coming from Light-Tail distribution like the sub-Gaussian, then we can establish the convergence results of this algorithm. In particular, we can show that the difference between Wik plus 1 and Wik squared is decreasing in the order of tau k squared, and to power 4 is decreasing with the power of tau k to power 4. By using this result, we can establish the convergence results of the algorithm, and we can show that if tau k is same as before, 1 over square root of n, beta k is fixed depending on the problem parameters, we can get the sample complexity of this algorithm, the multi-level nested averaging, the multi-level linearized nested averaging stochastic gradient method, as rho hat to power t, which rho hat is the problem parameter, essentially the Lipschitz constant, which is in the order of something to power t. So this rho hat to power t is in the order of the Lipschitz constant of the composite function. T to power 6 divided by epsilon to 4. And this is the same sample complexity for estimating the function values. So as you can see here, the dependence on epsilon is 1 over epsilon to 4, which is the same as the dependence of the classical stochastic optimization, where you just have one expectation. So here we have shown that it doesn't matter you have 2 or more functions in the composition form, we can still recover the optimal rate of 1 over epsilon to 4. However, there are some dependency on the number of layers, t. So I don't think that we can improve this part because, as I mentioned, this rho hat to power t is in the order of the Lipschitz constant of the problem. So I can just remove that one and set it as the Lipschitz constant of the problem. But there might be some possibility to improve the dependence of this, to improve this 6. But we still don't know. But we know that the dependence on target accuracy, epsilon, is optimal for this algorithm. So as I mentioned, the dependency on epsilon is unimprovable. The algorithm exhibits the level-independent behavior, and its convergence analysis is the same for both constrained and unconstrained cases. And the algorithm does not require boundedness of the feasible set or batch of samples per iteration. So that's make the algorithm practical for online problems, that it might not be a good idea to take a batch of samples per iteration. Okay. So I think this was my last slide. Thanks for attention. I would be happy to take your questions if there is any.
Thank you, Dr. Kadimi. It was a very interesting presentation. So we have reached the QA session. If anyone had any questions, please either type it in the related box or raise your hand so I can activate your microphone. So until people remember their questions, I'll ask you a question, Dr. Qadimi. I wanted to ask you a general question. As I see that you are at the Management Sciences Department. So because we have a lot of undergraduate students in this webinar, can you give a couple of examples of how machine learning methods and your related work are used in a managerial setting? Like how is this, like we know this, in the optimization phase in computer science, in other areas, but can you give a couple of examples of how this can be used in a in management sciences and what problems can be solved using it?
Yeah, so I provided some examples at the beginning of this talk, which were essentially examples from the machine learning problems. But there are some, not this algorithm, but I have been working on some other algorithms that can be used, for example, for sequential decision-making problems. One specific example is energy storage problem that I have been working on that over the past couple of years. So I can just briefly mention this one. So this is essentially an inventory problem with the case of the rolling forecast. So for example, assume that you have a wind farm and you have access to the main power grid, and you are a smart grid manager. So you want to see at each hour how much buy from the main power grid, how much use from the wind farms, and how much to store to use in the next hours. So the difficulty of this problem is that at each hour you have a forecast for the available winds, but it is very stochastic. So, and it is changing every hour. So this is the problem, class of problem that we call it the sequential decision making under rolling forecast. And it is essentially an inventory problem, meaning that it can be, this problem setting can be applied to any inventory problem which you have a rolling forecast. So you want to forecast some uncertainty in your problem for your inventory system, but that forecast is not fixed. So it will be changing from time to time. For this energy storage problem, it can change even 5 minutes to 5 minutes. So there are some algorithms. So I have been working on some approach to solve this problem, which we call the parametric cost function approximation, that you design some algorithm to solve this problem such that you train your algorithm, you train your model with some parameters that those parameters capture the uncertainty in the problem. So I'm not going into details of this one, but I can say one specific example related to the management sciences is just these inventory problems under the presence of the rolling forecast. Another example, I would say, for example, the risk management may be related to the management sciences. So the risk management problems can be formulated, as I mentioned at the beginning of this talk, as the composition problems. And one can use this algorithm or some other algorithms, because in some examples, you don't have access even to the stochastic gradient. You need to run some simulation process to get an observation for your objective function. So there are some zeros order variant of this algorithm that I'm currently working on that, which we assume that you don't have access to the stochastic gradient. You just simulate the system and then observe the value of the objective function. So based on those values, you estimate the gradient of the objective function, and then you design some algorithms to be convergent for your class of problems.
So any other questions? دوستان اگه سوال دارن حالا دیگه میتونن بپرسین. Miss Muti, please, you can activate your microphone and ask your question.
Do you have my voice?
Yes.
Okay. Thank you for your presentation. Actually, I recently started my master thesis on deep generative models. Although the details are still unclear for me, but it would be great if I know the way I could make connection between your improved method and deep generative models, and to know where's the starting point. Thank you.
You're welcome. So if I go back to the slide that's, I don't know, let me see. Maybe it's somewhere here. Yep. So the case of the generative approach for compressed sensing that I mentioned is that, so people have shown that for compressed sensing, instead of the this classical formulation, people proposed this formulation which used neural net to formulate the problem for compressed sensing. So in the paper that I mentioned here, as I remember, I'm not sure which method they use, or even they use any method to solve the problem, or it was just a formula remodeling of the problem. But this algorithm here can be used to solve this problem. I mean, the last algorithms that I presented, the multi-level case. Because for this deep neural net, when you have a composition of some functions, it is almost impossible that you come up with, for example, convex function. Your function, your model, this G would be essentially non-convex. So this is the first point when using this deep neural net for compressed sensing. And the second one is how to solve this problem. As I mentioned, I don't remember, I have to look to this paper again, but as I know, the algorithm that I presented here would achieve the first sample complexity for this multi-level case, which as one example is this one. But the point here is we have not implemented our algorithm. So it would be a good idea to implement that algorithm for solving this compressed sensing by using the deep neural networks. So I think this is something that we have to do, because theory is something, you design some algorithms and you show that they are convergent, but in practice, you have to make them work. So I think one good example of research, at least for us, is to show that our algorithm works in practice. And I think this one would be a good example. So you can look at this paper. I don't know you have seen this one or not.
I would definitely take a look at this paper.
And then you will see this reformulation. Maybe there are some others using this generative approach to other problem, not just compressed sensing. But this is the example that we found in the literature, and we believe that our algorithm is a good fit for solving this one. But still, we have not implemented our algorithm. So I don't know if we implement it, then we get a better answer than, for example, approaches in this paper or other paper, the result they get for solving this problem or not. Theoretically, we can, but practically, I don't know.
Thanks a lot. Thank you.
You are welcome. So there is a question here I can see. Have you tested this algorithm, and what is your platform for implementing such algorithms? So I only tested the NASA method for the two-level case. I mean, not for the two-level case. It was essentially for the one-level case, but I applied that one under the zeros order setting that I mentioned. So actually, I applied that one for solving that energy storage problem that I mentioned. So for that one, that was an inventory problem. So to get an inventory cost of the system, we had to simulate the system and get an unbiased estimator for the value of the inventory costs. And then we estimated the gradient based on that observations from the simulation. And then we had the numerical experiments. For that problem, I can say that the special case of the NASA method works well in practice in comparison to the, for example, the zeros order version of the stochastic gradient method. I would say that that zeros order NASA method works well in practice for that particular problem. But as I mentioned, just to the I don't remember her name, but as I just mentioned, we have not tested these algorithms that much. So this is something that we need to do. But for the inventory problem, that energy storage problem, it works well, and it is something that we expect because I'm not sure I mentioned this in the talk or not. We don't have the mini batch of samples to reduce the variance with the stochastic gradient, but we take a weighted average of the stochastic gradient. This is essentially an online variance reduction technique that we use in this algorithm. And that's why we don't need the batch of samples for the constrained case. Because one common practice for non-convex stochastic constraint problem is to take a batch of samples to reduce the noise associated with the stochastic gradient. But we use the online variance reduction technique, and we observe that one in solving that inventory problem, that when you run the algorithm for many iterations, you have different runs, the difference between the output of the algorithm, the variance of the output is much less than the case that you just solved the stochastic gradient method.
Thank you, Dr. Qadimi. I think we've come to the end of the QA session. I would like to ask the participants to follow the Google form link that Mr. Mohammed has provided. We would like to hear your feedback on this webinar and other webinars that we had, so we can continually improve them. So I think that I can switch to Farsi.